Hello class, I hope everyone is doing well today. We're going to start learning about a new topic called moles, and then we'll even practice how to use them in our conversions. So this is what we'll get started on. As always, I like to ask you guys some questions to get you thinking about what we're going to learn about. So our first question is, how can we find the amount of atoms in a substance? So our atoms are a very small thing that we learned about, and they are very hard to just count. So it's not as easy as saying how many cards are in a deck of cards because we can't see them. So how could we find that out? So if you guys have any ideas, please let me know. I think we could find them out using a conversion now. So any conversion that we've been practicing, well, not any conversion, but like the conversions we've been practicing, we could say there are so many atoms in this amount of substance. So, also, when would it be important to know how many atoms are in a substance? Why would we even want to find this? So we said we can find it by a conversion, but why? I was thinking it's very important for our chemical reactions. So if we want to know how much is going to react in something, so for example, if we wanted to know how much sodium to put with our chloride to make salt, this is how we would find it out. Some of our objectives, by the end of the day, we want to be able to describe what a mole is. We want to be able to understand how to use moles and Avogadro's number in simple conversion. So those are our two objectives. I have this video linked in our classroom. As always, it does a great job explaining what a mole is. So please pause this video. I think it makes more sense to listen to this video and then the rest of my presentation. So please watch this video. It's not very long, only 4 minutes long, but it does a great job. So, a quick note, just wanted to talk to you guys about scientific notation first. So, if we have numbers that are really big or really small, we, as scientists, made up a way to write them so that it's easier to see and read. So, for example, we'll use, or how we do it is we use one number and then one number before the decimal, and then we'll multiply it by 10 to some power. So 10 to the power of x. So this could be 10 to the power of 2, which is 10 times 10. 10 to the power of 1 is just 10. Or even 10 to the power of 20, which would be 20, or it'd be 10 times 10 times 10 times 10 times 10 times 10 times 10, all the way for 20 times. So for example, if we wanted to write 50, the number 50, in scientific notation, we would write it as 5.0 times 10 to the 1, because 5 times just 10 is 50. So when we read this, 10 to the power of 1 is 10, and 5 times 10 is 50. So that's how we would write it in scientific notation. Another one is if we had the number 0.5, we would multiply 5 times 10 to the negative 1, which really means that we're going to divide. So this means that we're going to divide anytime we see a negative. So 5 divided by 10 is 0.5. So it doesn't make too much sense to write it this way. This looks a lot more complicated than our numbers over here, but it's really helpful for really big and really small things. And this happens a lot when we talk about something small like atoms, or something really big like the outer space. We like to use these scientific notations. So we will be seeing some scientific notation, so I just wanted to explain it to you guys. But what we're going to talk about is what are moles. So a mole is a specific amount of something. It is a lot like a dozen. So if you guys have ever heard a dozen used, a dozen means that there's 12 things of something. I usually think of donuts. A dozen donuts is an often thing that gets sold. But 1 mole is 6.02 times 10 to the 23rd. So 10 to the 23rd means we have 10 times 10 23 times. So it's a very large number, and that makes up 1 mole. So just like a dozen, we can use this 6.02 times 10 to the 23rd of a lot of different things. So, to see this number written out is actually like this. It's 602 hexillion, or this big long zero with a lot of, or this big long number with a bunch of zeros. So that's why we write it in scientific notation, because it looks a lot shorter and easier to read. This is also known, this 6.02 times 10 to the 23rd, as Avogadro's number. And so, for example, how many donuts are in 3 dozen donuts? We've been practicing conversions. So if we have 3 dozen donuts, 1 dozen, we can cancel our dozens. So then it would be 3 dozen, or 3 times 12 donuts is 36. So there are 36 donuts in 3 dozen. We'll be doing this, but just simply with this bigger number for our moles. So let's look through our examples. How much space do you think 1 mole of basketballs would take up? 1 mole of basketballs. If we had 602 hexillion basketballs, how much space would it take up? It'd actually take up the size of the Earth. So that's how big this number is. It's huge. How long would 1 mile of donuts stacked on top of each other go for? So if we tried to measure the length of a bunch of donuts stacked on top of each other, 1 mole of donuts stacked on top of each other, it would go to the sun and back 2 billion times. So the sun is a really, really far way away, and we're still going 2 billion times there and back. How much space would 1 mole of carbon take up? It's about 1 small dish like this is 1 mole of carbon. So because carbon atoms are so small, we need really big numbers like these moles to get any decent amount that we can use, any good amount that we can use. If we were to do a mole of something big, it just would be, we wouldn't be able to handle the amount it is. We wouldn't be able to handle as many basketballs as the Earth is big. But because our atoms are so small, we need to use a big number. We need to use a lot of little, really, really small things to get anywhere. So that is the idea behind a mole. But why does it matter? So moles can be used to find the numbers of atoms in a substance. So again, a mole of anything is equal to 6.02 times 10 to the 23rd particles of something. So, for example, how many atoms are in 4.5 moles of carbon? Well, we can do a simple conversion like we've been practicing. So, we can take 4.5 moles of carbon, and then we said 1 mole of anything is equal to 6.02 times 10 to the 23rd particles, or atoms. So that's all I did. This is a simple conversion. It's just with a big number. So, I said 1 mole, so I put it on the bottom so that our moles of carbon are going to cancel, is equal to 6.02 times 10 to the 23rd. And then our moles of carbon are going to cancel, and I multiplied 4.5 by 6.02 times 10 to the 23rd to get 27.09 times 10 to the 23rd. So that is all that we needed to do. But now we know how many atoms, individual carbon atoms, there are in 4.5 moles. I also like this little picture because oftentimes we get confused with a scientific mole and the animal mole. And so I thought it was funny because it says, "Don't laugh, you'd be ugly if you were composed of 6.02 times 10 to the 23rd particles too." So they're making a joke about the different moles. It's like homophone. It's a homophone, I think is the correct word. So it's spelled the same way, sounds the same, but 2 different things. I think Mr. Justin has been teaching you guys about those. So we can go the other way though too. We can find the number of atoms given the number of moles. So for example, we can find the number of atoms given the number of moles. I think I switched that around. We can find the number of moles given the amount of atoms. So, for example, how many moles are in 4.72 times 10 to the 24th atoms of nitrogen? So, again, a simple one-step conversion. We start with what we're given. We're given 4.72 times 10 to the 24 atoms of nitrogen. We need to put our Avogadro's number, our big number on the bottom here, our 6.02 times 10 to the 23rd atoms of nitrogen, and then 1 mole of nitrogen on top. We simply will divide them across and get 7.84 times 10 to the 23rd moles of nitrogen. So, some more examples. If you wanted to know the amount of hydrogen atoms in a water bottle, how could we find it? Well, first, we need to know how many hydrogen atoms are in 1 molecule of water. So in H2O, which is our molecular formula for water, how many hydrogen atoms are there? Well, there's 2, because we have a little 2 next to our H, so we have 2 hydrogen atoms. How many hydrogen atoms are in 5 molecules of water? So in 1 molecule of water, we have 2, but now we have 5 molecules. So if we did 2 times 5, we would have 10. So we'd have 10 hydrogens. 10 hydrogen atoms. So now about how many hydrogen atoms are in 1 mole of water? So we can do a conversion here as well, where we say 1 mole of water. So we can do a conversion like we've been practicing. So we have 1 mole of 1 mole of water, H2O, and to get rid of our moles, we have to get to molecules. So we can say 1 mole of H2O so we'll put 1 mole of H2O on the bottom, so these two things cancel, and then we'll use Avogadro's number on the top. So we're into molecules. Our unit that we have left over is molecules, but we want atoms of water. So atoms of hydrogen in water. So we can now say that for every 1 molecule of water, there are 2 atoms of hydrogen. And that means our molecules of water will cancel, leaving us with atoms of hydrogen. Once we multiply them all across, our answer would be 1.2 times 10 to the 24th. So, we can do lots of different things and simple conversions, understanding moles. I like to think of them again as just like a dozen, or another way to say a certain group, a certain amount in a group. So, if you guys have questions about that, please let me know. We will be doing lots of practice with these coming up.